what happens when you apply gate voltage to the MOS structure. So here we consider the bound model where you have the p-type doping in the substrate of the silicon. So where you have a hose and then the negatively charged the boron acceptors. So when you apply positive voltage to the gate here, so then the hose will be pushed away because the holes are positively charged. So then what is left here is this depletion region with the acceptors, and the acceptors are negatively charged, so you have this Na minus. So with higher and higher voltage, then you are going to increase the depletion width, and then to a certain point where you reach the threshold. So when you reach the threshold, then here at the surface of the silicon to the oxide interface, then you will have this inversion. So now you get electrons here, and the surface becomes N-type, but still the bulk substrate is P-type. Only the surface becomes N-type. Typically, this surface means like a few nanometer thick, one layer. Let's say one layer of the surface, which is a few nanometer thick. So we are going to get one more surface electrons. So this is when the gate voltage is higher than threshold voltage. And then we look at how the band bent during this process. So to create this inversion, here the conclusion is that we need to move down the the EC by 2 phi b. So what is this phi b? This phi b is the distance between the Fermi level to the intrinsic Fermi level, which is middle of the band gap. So you can get this phi b by using this equation. Essentially, it's determined by the doping density Na, because the doping density will determine the distance from the Fermi level to the valence band edge EV. So the higher doping, then this distance is smaller, so phi b will be larger. So then this band bending from at the surface, we call it the surface potential. And then this surface potential needs to be pushed down by phi s, which is 2 phi b at the threshold voltage. So at this condition, then the surface electron density will equal to the substrate hole density. So this is the condition we define as the threshold. And then the surface potential or the band bending at the surface will be 2 phi b at the threshold. And then we have the 4 scenarios here for the MOS band structure. So initially, it's a flat band condition where we assume the metal Fermi level is the same as the silicon Fermi level. So initially, we assume this flat band condition. And then if the gate voltage is negative for this MOS structure with the P-type substrate, so the negative voltage will pull up the Fermi level to the metal. Because this negative voltage is applied to the metal. And then the other band will bend up like this. So here, in the valence band, you will get more holes. So holes are the majority carrier in the P-type substrate. So it's like more holes are accumulated at the surface. So this is accumulation. And then if we make the gate voltage larger than 0, but smaller than the threshold voltage, VTH, then here we are going to push down the Fermi level of the metal. So all the band of the oxide and the surface of the silicon will bend down. And then here those holes will be pushed away. So we have the depletion region here, where you don't have the free carrier. That means you don't have the holes or electrons. So this is like depletion. But when the gate voltage is large enough, let's say larger than threshold voltage, so this band is so bent that this Fermi level at the surface is close to the conduction band edge EC, where you induce the immersion of the electrons. So then you will have the electrons in the surface. That is the inversion. And then here we go through this derivation to get the threshold voltage, the equation for the threshold voltage. So the basic idea is to look at the condition for the threshold, which is when you bend the band down like this to the blue curve, where the surface potential here, phi s, which is the band bending at the surface, this phi s equals to 2 phi b. So that is the condition. So here we use the derivation from the charge density to the electric field. So this is when you do one integration, then you will get the electric field from the charge density. So here we have the depletion charge Na minus here, but we need to get the total number of charge there. So you need to do the integration. Or in other words, you need to look at the area under that function. So you will get the electric field. And in the silicon, the electric field is linearly decayed from the surface to the edge of the depletion region. While in the oxide, the electric field is a constant. And then you do one more integration from the electric field, you will get potential, because voltage potential is the electric field built up over some distance. So here, if you do one more time the integration, so the linear function will become parabolic function, and then the constant electric field will become linear drop of the voltage potential here. So then you can get the equations like this. So then you get a function of the surface potential as a function of the W, the depletion width. And the applied voltage, that is the gate voltage Vg, so has two components. One is the voltage drop across the oxide, the other is the voltage drop in the silicon. So in the silicon, that means the surface potential here. So then we will calculate this with oxide using the depletion width, because we here assume the total charge over the oxide capacitance. So that is the voltage across the oxide, and then plus the phi s. So plug in the W as a function of phi s, then we'll get the eventual form of the gate voltage as a function of phi s. And we know the condition for the threshold is when the phi s reaches to 2 phi b. And then we plug in the 2 phi b here, eventually we will get the threshold voltage equation like this. And here, I don't require the derivation, but we need to understand the dependency of the threshold voltage as those parameters, as a function of those parameters. For example, here what matters is NA, right? So the doping density, let's say, the higher doping density, let's say the larger or smaller the threshold voltage is. Right? From here, from the equation, you can see that higher doping, larger threshold voltage. And actually, this phi B also depends on NA. Right? This phi B actually also depends on NA. You will also notice that when you increase NA, phi B will increase. Why is that? If you recall, here is Venn diagram. If you increase the doping density NA, so the Fermi level, will be closer to the valence band edge EV. That means phi B is larger, right? So higher NA, larger phi B. So here higher NA, larger phi B, and also here NA is shown here. So that means larger NA, larger phi B, larger NA. So all the terms here go up. Your threshold voltage will go up. And other parameters, and also here phi B go up. So other parameters like the epsilon, this is epsilon silicon. Those are the constant value. Q is the charge quantity, so what matters here is the doping density. Higher doping density, larger threshold. Of course, the other term here is the COX. That is the capacitance of the gate oxide. And we discussed that this capacitance depends on the thickness of the oxide. So it's the epsilon oxide divided by the thickness, TOX. So the thinner the oxide, the larger the capacitance. So if the larger the capacitance, then here you see smaller threshold voltage. So any questions? Yes?
What is V of OX? Is that, because V of T is the threshold voltage, right?
What is VOX here? So VOX is the voltage drop across the oxide. So your gate voltage, you apply the gate voltage to your metal, and this voltage needs to drop across the oxide and cross the silicon depletion region and then go to the zero ground. So VOX is the voltage drop across this oxide. So the gate voltage you apply has two components. One is the VOX, the other is the phi S. Because you need to drop the voltage across the oxide first, and then the silicon, and then ground.
What is the VFB?
VFB is a flat band voltage, where we assume to be zero in our derivation. But in reality, due to different metal or different semiconductor, so the VFB is defined as the metal work function minus this bias is different. Okay, so this one is the distance between the vacuum level to the Fermi level of the semiconductor. So if there's no difference here, then the VFB equals to zero. Or in other words, if we assume initially the Fermi without any voltage, the Fermi level of the metal is the same as the Fermi level of the silicon, then we assume the VFB equals to zero. So this means the VFB equals to 0. So if this initial condition does not satisfy and this VFB equals to 0, then this difference between the Fermi level between metal and the silicon will be showed up in the final threshold voltage. But I think in this class we assume that this VFB equals to 0. Alright, so let's look at some of the real simulation results. So here we are going to show the 3 variable, the charge density, and then the second one is the electric field, third one is the electrical potential, voltage potential of this MOS structure. So where you have the metal oxide and the p-type substrate, and then the p-type doping, Na, in this case is 10 to the power 18. So here we are going to show the real simulation results of those variables as a function of the gate voltage you apply. So initially here the gate voltage equals to 0, and the phi b in this case, due to this doping, you can calculate what is the phi b. Once you are given the doping density, you can calculate what is phi b from the band diagram. And in this example, given this doping, 10 to the power 18, then 2 phi b will be this 0.93 volts. So this is what you can calculate. And now we assume the gate voltage VG equals to 0 to start with. Okay, so then we'll show some animation in the next. So let's say, if now we apply the gate voltage to be this 0.21 volts, which will give you the phi s like 0.1 of the 2 phi b. So if you apply the gate voltage like this 0.21 volts positive, then you will see the charge build up here. So let me ask, what are the charges here? Let's say this is this corresponds to this structure. So this is metal, this is oxide, this is the silicon side. So here we have the negative charge. So what contributes to that negative charge?
Electrons.
No.
Because that voltage pushed away.
Yeah, because those are pushed away, so we have the acceptor, the dopant, the Na minus left over there. So this is the real simulation result. And then you see the electric field a little bit here, because now the voltage is kind of small. And then the voltage drop. This is this 0.21 volts. And then this voltage will drop in the, because as we said, this gate voltage has two components. One is VOX, one is phi s. You see this 0.21 volts is dropped across the VOX, which is the oxide, and then the phi s, which is the surface potential of the silicon surface. So this is the simulation results, and then we are going to play the animation. So you can see as we increase the gate voltage, what will happen. Okay. So I will play this. Just watch this. So now increase to 0.44 volts of the gate voltage. Phi s now is a quarter of 2 phi b. So you see the difference here, from here to here. So the difference, you see that this depletion width increase. Right. So this is still in the depletion condition because phi s is just a quarter of 2 phi b. Okay, let's keep increasing the gate voltage. So you see the depletion width further increase, further increase, further increase. So and here you see the voltage keep going up, but no matter what, this voltage will drop between the, let's say, across first this oxide part, and then the phi s, which is, I would say the VOX actually is this part, and phi s is this part. So you have this gate voltage. In total, you apply like this 1 volt, and then part of that drop across this oxide, and the other part drop across the silicon as a phi s. So now here the phi s reached to 0.7 to phi b. Still is not threshold yet. So this is 0.8 to phi b, 0.9 to phi b. Okay, so then the next one is where the magic will happen. You see what happened? Now this phi s equals to 2 phi b. So this is a threshold condition. And you see what changes here. What is this? So what's this? Any idea? This is a charge. So now you see this spike in that charge density. So what is that spike?
Inversion. No.
Inversion, yeah, electrons. So those are the electrons, because electrons are negative, so that's why it's pointing down in the charge density. And it is just to the surface, so that's why it's just a single layer, very thin. In reality, it's just a few nanometers to the surface. So you are going to build up the charge, inversion charge. So this is the threshold condition. And now this gate voltage is defined as the VTH, threshold voltage. In this case, this is 1.38 volts. And now this is like the maximum depletion width. So this is the condition for the threshold. Now if we further increase the gate voltage, then what will happen? You will see that here we further increase the gate voltage. Now it's 1.3. Now it becomes 1.46. Now it's 1.67. So we keep increase the gate voltage, and even let's say 2.2 volts. So you are going to get more and more inversion electron to the surface. This is the first observation. The second one is that if you look at the maximum diffusion width, does not change too much here, from here to here. You see, this one does not change too much. Almost no change. We are going to get more and more electrons here. And another observation is that the phi s actually does not change too much. If you compare from here, this is threshold voltage. Now we have the phi s, which is this one. This is exactly at 2 phi V. And then we'll keep increase the gate voltage. This phi s does not change too much after the inversion, after you reach the threshold. But you are going to get one more gate voltage here. This is your gate voltage. Now even the gate voltage becomes 2.2 volts. You see that the phi s is just 1.15 times 2 phi V. So it does not change too much.